College Algebra, Chapter 5, Section 6, Further Applications and Modeling with Exponential and Logarithmic Functions. Our first application is going to be exponential growth and decay. An exponential growth or decay function looks like this. A of t equals a sub 0 times e to the kt, where a sub 0 represents the initial quantity present, in other words, the amount of whatever substance you're starting with. T represents the time, how much time has elapsed, and that could be in seconds, minutes, days, hours, months. It just depends on what we're talking about. K represents the growth constant when it is positive, but it represents the decay constant when it's negative. So if that power is positive, the function will be growing, and if it's negative, it will be decaying. A of t represents the amount of present at a given time t. The exponential growth function increases over its domain, which is what you would expect if it's growing, while the exponential decay function decreases over its domain, again, what you would expect. And we usually restrict t to being non-negative, giving our domain 0 to infinity, because really it makes more sense for time to be in terms of positive numbers. Okay, these are what the graphs of the growth and decay function would look like. The growth would be on the left and the decay on the right. Let's try a problem. Carbon-14 is a radioactive form of carbon found in all living plants and animals. After a plant or animal dies, the radiocarbon disintegrates. Scientists determine the age of the remains by comparing the amount of carbon-14 present with the amount found in living plants and animals. The amount of carbon-14 present after t years is given by A of t equals a sub 0 e to the kt. That's our formula we started with k being approximately negative natural log of 2 times 1 over 5,700. And it's negative indicates it's a decay function. If the fossil contains 1/5 of the carbon-14 contained in a contemporary living sample, estimate the age to the nearest 1,000 years. All right, if you want to give this a try, pause the recording and go for it, and then resume to check your answer. Here's our solution. We want to know, we know that there's 1/5 of the amount it started with. So 1/5 a sub 0 equals a sub 0 times e to the negative natural log of 2 times 1 over 5,700 t. Those are the numbers they gave us for k. The a sub 0's cancel out. And then what we're going to do is take the natural log of both sides to remove the e. So we have the natural log of 1/5 equals the negative natural log of 2 over 5,700 times t. And then we're going to multiply both sides by the reciprocal of that fraction and put it in our calculator and end up with about 13,235. So about 13,000 years. Now we're going to work with half-life. Links posted on Twitter generally experience half of their hits h within the first 2.8 hours. This pattern continues over time so that the number of hits on a link decreases by half over each 2.8 hour period. Hits on a Twitter link decay according to the function h of t equals h sub 0 e to the negative kt, where t is time in hours. Find the exact value of k and then approximate k. Okay, pause the recording, give it a try, and resume to check your answer. Okay, for our solution, the half-life tells us that when time equals 2.8 hours, then what we have remaining, the number of hits remaining is 1/2 what we started with. So we're going to fit that into the equation. So h of t equals h sub 0 e negative k to the 2.8. H of t is 1/2 h sub 0. That means that the h sub 0's are going to cancel. And then we're going to take the natural log of both sides. The natural log and the e cancel out. So we have the natural log of 1/2 equals negative 2.8k. And then divide by negative 2.8. Put it in your calculator and you get 0.24755. So Twitter links decay according to the equation. H of t equals h sub 0 times e to the negative 2.4755 t. Another application of logarithms is in sound intensity. The loudness of sound is measured in a unit called a decibel. To measure with this unit, we first assign an intensity of I sub 0 to a very faint sound called the threshold sound. If a particular sound has intensity I, then the decibel rating of this louder sound is D equals 10 times the log of I over I sub 0. The 2013 Super Bowl and the Superdome reached levels of 10 to the 12th times I sub 0. Find the decibel rating of this event and compare it with the average rating of 80 decibels for a ringing telephone. All right, pause the recording and give this a try and resume to check your answer. We're going to replace I with 10 to the 12th times I sub 0. The I sub 0's cancel out, and we have 10 times log 10 to the 12th. Well, the log base 10 of 10 to the 12th is 12. Multiply 10 times 12 and we get 120. The sound levels reached 120 decibels, and that is equivalent to 10 to the 12th I sub 0. 80 decibels is equivalent to 10 to the 8th times I sub 0, so the ratio 10 to the 12th over 10 to the 8th gives us 10 to the 4th, or 10,000. In other words, the noise in the Superdome was 10,000 times the intensity of a ringing telephone. Okay, now let's do a problem that takes us back to our compound interest equation. How long will it take $1,000 invested at 6% interest compounded quarterly to grow to $2,700? Pause the recording, give this a try, resume to check your answer. So we have A is 2,700, P is 1,000, R is 0.06, and N is 4. And putting everything in the equation, we see that our variable is indeed an exponent. So what we need to do is we need to divide by the 1,000 first, and that gives us 2.7 equals 1.015 to the 4t power. They combined the 1 plus 0.06 over 4 to get that. The next thing we're going to do is take the logarithm, and it can be the logarithm or the natural log, it doesn't matter, of both sides. That allows us to bring the 4t out of being a power and down in front, then divide by the log of 1.015. And so we have log point of 2.7. We're also going to divide by the 4 over 4 times log of 1.015. Putting that in the calculator, we get 16.678, or about 16 3/4 years. If a quantity grows exponentially, the amount of time that it takes to become twice its original amount is called doubling time. This is similar to half-life for quantities that experience decay. The initial amount present does not affect the doubling time or half-life. As we've seen that before, with half-life, the initial amounts always cancel out. The same is going to happen with doubling time. And we're going to do basically the same process. The amount we're going to have is going to be 2 times the initial amount. So how long will it take the money in an account to double if it's compounded continuously at 3% interest? Again, use the same principle we used with the half-life, but instead of 1/2, use 2. Pause the recording, give this a try, and resume to check your answer. Our favorite formula here, PERT, our continuously compounding interest formula. The amount we're going to end up with is 2 times what we started with, so 2p equals pe to the 0.03t. The p's divide out, then we're going to take the natural log of both sides and divide by 0.03, and we get 23.1 years. Now we're going to solve the equation 7 times 1.01 to the x minus 2011 equals 8. This is going to estimate the year when the world population may reach 8 billion. Pause the recording, give it a try, and resume to check your answer. Okay, so the first thing we're going to do is we're going to divide by 7. Then we're going to take the logarithm of both sides so that our variable can come out from being a power. We'll divide both sides by the logarithm of 1.01 and then add 2011. And our answer is 2024. The rest of this, the recording, is going to be some examples for you to try. So As you come to each one, pause the recording, give it a try, resume to check your answer, and then proceed to the next. Do this for the rest of the recording.